Hi, I'm Ryan Baker, and this is Big Data in Education, 10th Anniversary Edition. Today, we'll discuss algorithmic bias in education. So, what is algorithmic bias? One classical definition comes from Friedman and Nissenbaum, who say that biased computer systems systematically and unfairly discriminate against individuals or groups of individuals in favor of others. A working definition that I like, for obvious reasons, is Baker and Hahn 2022, which is cases where model performance is substantially better or worse across mutually exclusive groups separated by non-malleable factors. A non-malleable factor being something that someone, for example, in a school system can't realistically change about a student, such as their race or where they live. So, where does algorithmic bias come from? So one way to understand where algorithmic bias can come from is to look at the machine learning lifecycle, where we start at the top right with the actual world state, how things actually are. We determine something that we want to predict or infer, we collect measurement or data for it, we build a model to based on that measurement and data to make the prediction, and then we deploy it in the real world to drive some intervention. Now that intervention changes the actual world, which starts the entire cycle over again. A lot of algorithmic bias, and what I'll talk about today, comes from two steps. One of them is the actual learning of the model, and Kiselchek and Lee have a really nice review of that. And the other comes from the data and the measurement that we put in the model, and Baker and Hahn have a review of that. A key form of how bias can develop from measurement and data collection is representational bias, where the model performs less well for groups less well represented in the data used to develop the models. For example, a model mostly developed using data from suburban middle-class learners might then be used in an urban setting, and it might not work as well there. Now, people will sometimes say, I don't need to worry about that because I've got the full data, I'm not sampling. Well, that's great, but even a complete data set might not be enough if a specific group of interest is rarely seen in that data set. So how do we measure algorithmic bias? There's three broad approaches to doing this. The first is to test by group. We build the model and validate it initially with everybody, and then we try to take it by groups and split out the groups and say, how well does the model work for each group we currently have data on? A second approach is to cross-validate by group, where we build the model on some groups and then apply it to other groups and test on those groups. And this is a good approach for estimating how well a model works for groups that we don't yet have data for. A third approach is metrics that explicitly compare group performance to each other. In terms of metrics that compare groups to each other, there's three broad paradigms. Independence, which looks at whether there's statistical independence between the classifier's outcomes and group membership. The idea being that if the classifier's outcomes are dependent on group membership, you've got a problem. The second is separation, which says that an algorithm's decision has got to be independent of the group membership, conditional on the true outcomes. And the third is sufficiency, where true outcomes must be independent of protected attributes, conditional on the algorithmic decisions. Within the independence paradigm, you'll often see the metrics demographic parity and disparate impact, where demographic parity looks at the degree to which x is 1 given a being 1, minus the degree to which x is 1 if a is 0, and disparate impact is the ratio of those two things. Recently, people have started to talk about the metric MAD by Verger and colleagues, which can be seen as a generalization of demographic parity that takes the model confidence into account as well, not just binary classification. Within the paradigm of separation, the algorithmic bias community in general often talks about equal opportunity and equalized odds, where equal opportunity is the probability that x is 1 given a being 1 and also y being 1, minus that probability if a is 0 but y is still 1. And equalized odds, which is the equal opportunity averaged across outcomes y of 1 and y of 0, where we're not sure necessarily which is the better outcome, we just want to know that they have the same odds. A generalization of these is a BROCA, which is relatively more popular in learning analytics, which is the area of difference between ROC curves. And this can be seen, like MAD, as a generalization of other separation metrics while taking model confidence into account. Finally, for sufficiency, what we often see is a metric that's just simply called efficiency, which you calculate by taking the probability of the better outcome given the classifier's prediction and membership in the group of concern, and you take the difference between that and probably the better outcome based on getting that same prediction and non-membership in the group of concern. You subtract those two, take the absolute value. Other paradigms, and for a fuller discussion see Kiselchek and Lee, include similarity-based fairness, where you look for similar outcomes for students who are similar on features other than the demographic variable, and counterfactual fairness, where you look to see whether you would get the same outcome for the student if they're changed to a different demographic group, which typically you're going to see this one when you're actually doing something like using a demographic variable as a predictor, which is not something that I'd recommend. But metrics alone don't tell us the full story, because even if we establish that our algorithm is fair for our labels that we have, what if we don't trust these labels? And you say, wait, how can I not trust my labels? Like, if I can't trust my labels, what do I do? And this comes down to measurement bias, which occurs when we've got biases in our training examples used to develop the models. For example, judgment by other people might involve biases. Your coders might be looking at two people and using their unconscious biases when they make the labels. You might have this in judgments by people themselves. Really, anytime human beings are responsible for a decision, you have some risk of bias, and this includes so-called natural variables. For example, you might build a model to predict suspension from school, but suspension from school is itself governed by biases in the decisions of who gets suspended. So, okay, we've talked a little about the sources of potential algorithmic bias in education. What do we know about the bias impacting learners in common demographic categories? In fact, we don't know as much as we'd like to. Holstein and colleagues note that industrial teams often struggle to anticipate what subpopulations are impacted and what forms of unfairness they experience for specific kinds of machine learning applications. And most educational data mining research doesn't even mention learner demographics, much less investigate algorithmic bias in terms of it. See a review by Luc Paquette. But we do know a little bit, and I'd like to give a brief summary of evidence on algorithmic bias in education. And for full details as of 2021, an eternity to go for this stuff, see our article in the International Journal of Artificial Intelligence and Education, and for the very most up-to-date info, see our wiki at this link. Race and ethnicity. Several papers show that educational prediction algorithms perform worse for African American students and Latino students than students in other groups. And this includes predictions of grades, course failure, graduation, and dropout. However, other types of algorithms, like automated essay scoring and self-regulated learning detectors, have been found to be largely unbiased. It's worth noting, by the way, that in the United States, there's almost never enough data to test for biases impacting Native American learners, although see Christie et al. 2019. Now, as an important note, and I foreshadowed this a minute ago, many people argue for predicting explicitly based on race, but first of all, doing so can actually make the model less accurate in Renja Yu's work. And second of all, it can replicate biases in decisions being made by the instructors. And third of all, as Feathers noted, it can lead to blatantly discriminatory algorithms that make predictions based almost entirely on race. For an unbalanced, in-depth discussion of this issue, see our preprint, which you can find on the web. And as a note on our note, not including demographic variables as predictors is sometimes referred to as quote-unquote fairness through unawareness. But other variables can often secretly act as proxies for demographic variables, so fairness through unawareness is by itself insufficient. In my opinion, it's a good start, especially if you're then testing for algorithmic bias, but it's not enough always. Gender. There's been mixed, complicated results for gender, and it's been studied several times. Sometimes models seem to be biased against female students, and sometimes models seem to be biased against male students. Nationality. On a test of foreign language proficiency, one system inaccurately gave Arabic and Hindi-speaking students lower scores than human essay raters. In another example, models of help-seeking built using data from learners in the Philippines, Costa Rica, and the United States were each more accurate on students from their own countries than for students from other countries. And curiously, Costa Rica was much more the outlier here than the other two countries. And in a third example, models predicting standardized examination scores trained on data from the USA were more accurate for students in economically developed countries than students in less economically developed countries. And there's also evidence for algorithmic bias in education in terms of other categories like socioeconomic status, native language, disabilities, urbanicity, parental educational background, and even whether a student has a parent in the military. But there's still insufficient research about bias impacting other groups, and I would say that we don't even know about all the groups that are impacted at this point. The majority of empirical evidence for algorithmic bias in education has been published by researchers in the US, it's sad to say, and we need a lot more work to learn more about algorithmic bias worldwide. I've gotten critiqued by reviewers a couple times in my review articles for being US-centric. But the truth is that it's not really that we're trying to be US-centric, it's that the field is US-centric. We need much more work about algorithmic bias in the rest of the world. There's been a decent amount increasingly in Europe, but there's been surprisingly little in Asia, or Africa, or Latin America. Other takeaways from our survey. Models trained on one group of learners generally perform more poorly for new groups. Not surprising. There's been relatively little investigation of bias for many groups, and this is one of these cases where I really hope that this lecture will quickly become embarrassingly out of date. But I only know of one study involving Indigenous learners as of this recording. I don't know of any involving non-standard dialects or specific disabilities or non-binary and transgender learners or religious minorities. We need to know who's being impacted and how and when. And we know that if we do collect and train on a diverse sample of learners, our models are less biased. And that leads us to how can we address algorithmic bias? The answer is, first, we have to have better data, which actually is representative of students and which has demographic variables, though not as predictors. And then we have to actually check for algorithmic bias, and then we have to actually try to fix it. So there's a good discussion of this in Kizelchech and Lee 2022, and also maybe worth seeing Hort et al. 2023, although that paper lists methods more than focusing on which methods are best, but it's super comprehensive. Maybe the most common thing that people do is training separate models for each group, which is sometimes called compositional approaches. In compositional approaches, you train a separate model for each group. But there are some possible pitfalls. For one thing, what if some groups don't have enough data? Also, this approach explicitly treats members of different groups who are otherwise identical differently, and this can be seen as problematic in some cases. It can be seen as explicitly being biased. A related approach is to fit models and then adjust the output probabilities of each to match an equalized odds constraints. And this is also called calibrated equalized odds and has some of the same limitations, though not quite as obviously. One approach that's worth considering is data rebalancing. If one group is much less common than another in the dataset, we can use methods like SMOTE or data cloning to create a more balanced dataset. Now, this can only address biases due to unbalanced data, but that's a big part of it. Another popular approach is prejudice-free representation, where you iteratively process the dataset and fit separate models predicting both the target variable and the demographic attributes. And then among the features that predict the target variable, you iteratively remove the feature that best predicts each demographic variable, and you repeat doing this. You go back and you refit the models again, and you repeat it until the degree of fit to the demographic attributes is below some pre-selected cutoff. So what this produces is the best possible model for fitting your target variable while being under some cutoff for predicting the demographic attributes at the same time. Another very popular approach is cost-sensitive classification, which overweights errors on data points from groups where the model performs less well. And this can be used to improve the balance of the model accuracy between groups of learners. And there's been some demonstrations of usefulness for algorithmic bias, including specifically in education by Vasquez, Verdugo et al. And colleagues. And relatedly, sometimes people will look at adding a fairness term to the goodness estimate used during model fitting, which largely produces the same sort of results. And finally, people increasingly are thinking about adversarial learning, where one algorithm predicts what you want to predict, and another, called the adversary, predicts the sensitive attribute from its output. And you repeatedly retrain the main prediction algorithm to make the adversary less effective. The techniques for addressing algorithmic bias are getting better all the time, and I'm utterly certain that I will be re-recording this video in the next edition of this course because it's changing so quickly. And that's a great thing. I'm happy to see that. So this ends week 2 of Big Data in Education. Thank you very much, and I'll see you next week.